Thank you for the invitation. I'll try to present some thoughts about where HPC as a field, high performance computing is what you're going to hear me talking as HPC, and then consequently how that impacts some of the other scientific fields, as well as a few thoughts about COVID in particular. But before we define, actually, before we go into further, let's define HPC, high performance computing. So when we talk about high performance computing, what we refer to is the fastest computers out there, the computers that are capable of the most computational power. So these are computers, as you see on the left. This is the basement of the building that I work at or used to work at when we went to the office. This is occupied by a supercomputer. It's Cori. It is, I think, currently number 16th on the world list. It used to be eight or six or something when it first showed up. But the fastest computers out there, the list comes out twice a year, it's the top 500, and it changes about twice a year. Currently, the fastest one is in Japan that has 7,300,000 approximately computational cores. By the way, you can stop me with questions at any time. So this is what we mean about high performance computing. These are the computers that can tackle the most computationally intense problems out there. So what are some of those problems? These are basically any problems, scientific problems that are bound by compute power. I'm going to give you two concrete examples. One is climate forecasting. So climate forecasting traditionally has been bound by compute power because the models have been out there. The models, the mathematical models of how the weather interacts with other weather systems and they produce another weather system, for example, they've been out there. I mean, there's still research on it, but they're in a fairly good state. What has been limiting our weather forecasting capability is the resolution at which we can run these models. In other words, do we want to run the model at a detail of 10 kilometers? Like we consider a square of 10 kilometer square area to be 1 pixel in our model, or do we want to do the same with a 10-meter square or box? Treating it at a smaller resolution gives a much more detailed accuracy in climate forecasting. So the faster computer we have, the more accurate we get with weather prediction. But not just predicting the weather tomorrow, it's also predicting how the climate will be 10 years from now. So like long range prediction is part of the challenge. In fact, this image that I got here, it's trying to predict the climate at the end of the century. And another example is aircraft design. So Boeing, when they designed the new one, 787, the Dreamliner, what they were able to make use of more compute power than they had in previous designs. They were able to in more detail simulate the wings and all the other components. So not only did they design a more efficient wing, but they also were able to shave 200 pounds of the aircraft, which doesn't sound like a lot, but in production and scaling up and all the gas and everything, they were able to, that 200 pounds were translating to about $200 million in savings. So these are just two examples. There's a lot of more examples in bioengineering that I could talk about, but also a recent development that I'm sure you know is deep learning. And deep learning is, as a field, is starting to scale up and ramp up really quickly. This is a graph. This red line here is showing the computational demands of deep learning. And the x-axis here is time. The y-axis is computational demands. And the dark line here is the hardware performance. So our hardware performance has been scaling at this rate, whereas the demands that deep learning has, the compute demands that it has, are scaling way faster. Now, it could be because the field of deep learning in HPC is sort of starting still in some sense. But the point is, you can see the mismatch. Now, right now, if we were able to increase this hardware performance in the fastest computers that we have in the world, if we were able to increase it, we could make more accurate deep learning models, and this will have profound impact to any sort of AI for science and similar initiatives. Since And I also found this example in particular about COVID-19, a very concrete example how HPC was used. So there was a group of researchers that used a high performance computing system. I forget which one right now, but they were able to correlate genetic material of infected and non-infected control patients. So they were able to run 2.5 billion correlation calculations, and through those, they were able to see what enzymes were increasing or decreasing in people that were infected by COVID, and that explained some of the symptoms. So this is how we know some of the symptoms that are from COVID. Obviously, I cannot, explain to you the biological background from this, but the point is, they were able to search so much information using these high performance computing systems fast, and that's how we know some of the symptoms of COVID right now. There's a link if you want to find more information on the article on HPC Wire. So, as a field where high performance computing is going, the next major goal for the US and many other countries is what we call exascale computing. This is a copy paste from Wikipedia because many people haven't heard of exa uh, uh, before. So exa is like way above giga and mega and kilo and all the things that you might know from your phone. Like my phone has so many gigabytes of memory, where giga is 10 to the 9, exascale is 10 to the 18. So exa is giga squared, sort of.
I love the Yota name.
Yes, there's Zeta and Iota. We don't know what's coming next, so I mean, we probably won't see that anytime soon. But yeah, we need to have a meeting and decide. But anyway, this is the next challenge. And what I mean by exascale computing, that refers to a computer, one system that can run 1 exa floating point operations per second, meaning 10 to the 18 floating point operations per second. We are currently, so the systems that I showed you before are, the fastest system is about 40% of that. So, and that's the fastest system, that there's only one in Japan. The next one is about 10% of that. So there's still a huge performance gap that we need to close. And if we do that, it's going to have huge effects to a lot of scientific fields, like the ones I mentioned. The problem is that, so this is at what cost? So this graph here shows you on the x-axis you have time, years, and on the y-axis you have power. And you have 3 lines. So this is the average of top 10 and then top 50 and top 500. You can see that power, the consumed power that a system has, is increasing linearly with time. In fact, the number one system is above that. It's 28, I think, megawatts. I forget, so it's way above. So we could, in theory, build an exascale system right now. We could just copy paste and just build a huge system, but that would be way inefficient and way expensive. So part of the research, the challenge on the national labs and universities and everybody who's working on the HPC hardware design, as well as many companies, of course, is to design an efficient HPC system that has the same cost as HPC today, HPC systems today, but has higher power. And there's a lot that goes into this. Currently, our strategy, no, well, not currently, but like a lot of what people are trying to do today is efficiently just duplicate resources, make the systems larger, and that works. That gives you performance boost, but it's not a long-range solution. So where do we go from here? I, I'm sparing you all the technical details, but there are many sort of pieces to the problem, to the whole stack of making an HPC system, and there are many capable people working on the problem and trying to make HPC systems faster for all the reasons. One strategy is specialization. So nature has developed this powerful general purpose bird, but really it's a processor that I'm really referring to, that is very capable, but is also costly. You can't have many of them. On the other end of the spectrum, what we're working on these days is basically have many smaller birds. Each of them is not as capable, but you can have more of them. And that is the approach that we take with GPUs, for example. So we each GPU is not as capable, but we have more of them, and they're actually pretty good at specific workloads. So that's one strategy that we actually see in production systems right now. But moving forward, evolution is going to change our birds. It's going to make them capable of specific things. So now we're going to have different birds that are good at different things. In compute speak, so we're going from birds to computers now again. We started with this capable general purpose system. Now we actually have CPUs and GPUs sort of living in the same system, and that's sort of what's going on today. In the future, what we expect is accelerators. So we can have an accelerator that works on, I don't know, climate forecasting. We can have another accelerator that works on specific mathematical formulations like FFT or or anything that applications that we care about use. So that's sort of the near future, I would say. We expect to see that in a few iterations down the road of HPC systems. Way down the road, we expect heterogeneous systems, basically way diverse accelerators, way diverse memories, way diverse even transistors. We're looking into many different kind of new transistors and how we can integrate them on a system. The point that I'm trying to make here is that compute is slowly shifting from this nice homogeneous picture that we had before to something that is very specialized. And it's specialized for the workloads that we care about, because specialization is one way to gain performance. And then other people looking at exotic ideas. Don't need to worry about the details here, but I just wanted to give you a flavor of the exotic ideas that we also are working on. So one of them is superconducting computing. The idea is that if you look at a wire, its resistance grows linearly with temperature. But there's another class of materials called superconductive metals that if you cool them down to below a certain temperature, which by the way is really cold, it's like 4 to 20 Kelvin, depending on the material, they have zero resistance. So there's a lot of effort to take advantage of that zero resistance, because that means basically zero energy to compute. And it also means like tens of gigahertz of compute. We can get a huge performance over energy boost by using these um, materials. I think we can skip that. But okay, so this was just a flavor. And then really the field that we're playing with, like all the options that we have on the table of what is the next day for HPC or the day after the next day, like the future of HPC, is really diverse. And but we can sort of I try to group it in on this graph. On the one hand, we have more immediate solutions, which is partly specialization that I talked about. It's also new transistors, it's also new memories, it's also 3D stacking, and it's also other cool ideas that have been worked on a while, for a while, but they might mature at some point within the next 10 years. We also have more exotic ideas. Maybe 20 years from now, we'll see in production, in actual systems, some of the new transistors. For example, carbon nanotubes, that's or spintronics. They have promise, but they haven't really been demonstrated to anything other than the lab, and sometimes not even that. And then we also have in the middle new models of computation. And this is where we can fit machine learning accelerators, neuromorphic, quantum. There's a lot of options on the table. Each of them has their own timeline. Each of them is a different level of maturity. And we have to decide where to place our investments. So it's a really challenging field right now, which also means that it's really hard to predict what HPC will look like. Now, this is a scary thought. Let me walk you through this graph, but this is sort of like on the economic side of high performance computing. Because every time we have to design a chip, let's say that I'm running a company, I have a specific kind of computation that I want to accelerate in future systems, but being a company, I care about money. So for me to invest in a special chip just for my application, it needs to make sense. So on the y-axis here, we see the volume of the chip. So like if I design a chip, how many of them do I expect to make and sell? And then on the x-axis, we see the proposed or the speed up that I hope to get from specialization. Now, because a lot of the process of designing chips, the cost is constant, regardless of how many chips you're actually going to produce. The lower the chip volume, the more speed up we have to expect to get for it to be a good choice. So let's say that I'm gonna accelerate graphics. Well, everybody uses graphics. My chip volume is gonna be really high, so I don't need a lot of speed up. I'm in this blue region where if I compare my speed up compared to a homogeneous like processor that we have on our laptops, no, well, then I have to care about, well, how quickly is the general purpose processor going to be improving? Does it really make sense? And so on. But a lot of the applications that we talked about before, uh, COVID research or climate forecasting, these are not large markets. So these are applications that run in very few systems. So if a scientist wants to get a speed up of 10x, but their volume is really low, they just want to produce the chip and put it on a system so that they can run their code. That means that it might not be economically viable. So who's going to do it for them? So the scary thought that comes out of this is as computing gets specialized, uh, some domains, like some scientific domains, but also some commercial domains, might be left behind. We're going to have these big players who are capable of switching to specialized computing. Now, once they switch, they might no longer compute. I'm sorry. They might no longer invest in the general purpose computer research. So the people who are relying on general purpose computer research, now they're going to see slower progress. In that sense, they're going to be left behind. So we're going to be seeing potentially a diversified or fragmented computing field into the future, where the big players are going to be doing much better than the small players. Because right now, the small players are sort of tagging along a lot of the advances that are motivated by the big players. That's not going to happen anymore, or at least that's one expectation. And then also, when it comes to heterogeneous computing, this might be one of the more technical slides, but what I'm trying to say here is our systems right now, they run so many different workloads. And those workloads have so many different requirements. Right now, what we're doing is we're sort of trying to build one system to satisfy them all. So NERSC is the entity that runs the supercomputer that is in the same building as my office. It's basically, it runs Cori that I talked about before. They experience a range of scientific workloads in their systems. What they notice is that 15, so a minority of the workloads that they see uses 75% of the memory that they have available on nodes. So a vast minority of the workloads uses most of the memory, but half of the workloads use less than 15%. To put it more clearly, our systems right now are over-designed. They have more resources than most of what the applications need, and they do that because the applications that use all those resources, they're important. But moving forward, and as we scale up, that is not a strategy that we can keep going forward. So this might motivate more specialized systems. This might motivate a supercomputer for climate forecasting that is different than a supercomputer for aircraft design. Whereas now a lot of these workloads, they are running on the same system. All right, how am I doing on time? About 2 minutes left. I think we can skip that. We can go to that before I forget. So again, a COVID flavor. COVID, I mean, it had many impacts. It motivated a lot of AI-related research as well as data mining and a lot of I classify this as software, broadly speaking. Of course, it has many things, but like the Department of Energy and NSF, they gave in the US, and I'm sure other countries had something similar. They gave funding, short-term funding, for a lot of COVID-related research, which had been great. But I think the long-term effects of COVID on high-performance computing is that it brought many entities together on one hand. In fact, there was a consortium the COVID-19, the link you see at the bottom, that had companies, national labs, universities, they all came together to try to, for this common cause, use different, each of them, resources and expertise for this common cause, which I think has been a great sort of motivator. But also COVID-19 highlighted the need for faster HPC, because by building all these complicated AI models, we need this capable hardware so that we can, in the future, be better prepared to predict and react to pandemics. So that was largely a gap, I think, that COVID-19 highlighted. Sorry for that. My headset turned off right at the last slide. So in summary, HPC is a key enabler for many scientific fields. Many people don't think about it, but if we gave them, if we, like a lot of the partners that we work with, that work on the problems that I just talked about, if we gave them a more capable system, they would be more than happy to make their computation more demanding, so they can get more information out of their model. We are currently at crossroads when it comes to increasing the computational capability of HPC systems. There are currently so many options. It's hard to tell how HPC will look like in 30 years. But I think it's, with a certain degree of confidence, I can say that HPC will diversify, and that will create a bunch of implications that I led to, but it will also provide a boost of performance for future HPC systems that hopefully we can take advantage of. I think that's all I had to say. So let's start a discussion if anybody has any questions.
I'm unmuting myself to make some noise as usual.
Yeah.
Thank you so much. This has been a great presentation, George. I think you highlighted and you outlined the progress of high performance computing in a great way. Thank you so much. Let's proceed with questions from the audience. So feel free to ask.
I realized maybe it was a little too technical, but I hope that at least the message was clear of what we can expect.
I'm not the best one to judge because it's my field, so maybe someone that's not related can judge if it was too technical. I think it was okay personally.
No, I was just going to say I found it very relatable, but then I thought I should type it and I forgot to mute myself again. No, I mean, I think it was very interesting to learn. I'm not so far outside of the field. I was trained originally as an electrical engineer, so some basics are still tumbling around the head, but I never actually thought about the consequences of specialization of processors. And of course, I mean, it makes sense what you were saying. Totally, but it does give me some food for thought that really is the case, that just because everything has been gone, let me introduce the video. Just because so far everything has been gone to walking towards standardization in a way, and that there are great benefits to be gained from this, like electronics as well, but also the more classical. You have plugs, memory, any kind of hardware. We see this trend towards standardization, and for this reason, I've never thought about the benefits that can be gained from specialization. And I do agree that it makes sense, right? And then, of course, is the case when, well, if we are specializing things, what do we actually lose? So thanks for this interesting, yeah.
Yeah, I think that's a good point. Standardization, I think, was motivated initially by ease of programming. It was motivated by different reasons than increasing performance. In fact, it hurts performance in many ways. But priorities change, so we'll see what happens.
Well, I think it's also a question of how easy it is to make different things, right? Because originally, way back when, I'm not sure about this, I'm speculating, right? But packaging was difficult to make. So a lot of products had the same packaging, even though it was not optimal for them. And then with the increase of how versatile we can automate, how versatile can we make the manufacturing, what you call that, the production line, how easy can we customize the production line, makes making different things cheaper. If I can do it in the same factory, if I don't have to build one other factory in which I build this other type of packaging, then of course I can have different types of packaging from the same factory, which make, you know, serve their own different purposes of optimizing whatever they're optimizing over there. So if we are able to make hardware, if in the same facility, basically, I'm able to make different types of specialized hardware, I can have both the benefits of standardization, because the production unit, the unit that produced the hardware is standardized, but the hardware it produces, it's specialized for a purpose, right? But that still does not escape us from this problem that somebody can't just pick it up and put it together and produce a new thing, right?
Yeah, yeah, these are good thoughts. I mean, I can tell you there's a lot of effort to automatically design hardware for a specific application. What is less clear to me, because it's also largely about economics, is the fabrication part of it.
Right.
Like, how different does a chip need to be to require an entirely different fabrication run?
Facility, yeah.
Yeah, exactly. And I think what we may end up doing, because chips now can be large, we might produce one chip that has many of these accelerators, and they can cater to many of these scientific fields. So one fabrication run can have many accelerators if they're small enough.
But I mean, there is also this, like right now, you can develop a prototype on paper, and then you can have it produced in China, and that is accessible to you as a, you know, enthusiast to a certain degree, which was really not the case like 50 years ago.
True, absolutely. But then, I mean,
This
I
is
will
not
also
a
say,
this is not a, you know, an argument against what you were saying.
yeah,
It's just
no, no,
thinking aloud.
it,
Sorry.
it's a good thought, and a lot of these factors we don't know yet. So yeah,
Yeah.
you might be on to something, right? But I will also say that a lot of the cost of designing and making a chip is not the actual fabrication; it's the
Exactly right.
verification.
It's the yes, yes,
So
yes.
it's the human labor. If we find a cheaper fab,
Always.
that might not make it much cheaper.
Yeah, yeah. It's always the human labor that remains. I mean, this is very interesting, actually. It's like, on one hand, human labor is cheaper than automation, and on the other hand, human labor is expensive, and we cannot automate as much because human labor is expensive. So what I mean by this is that, I mean, a lot of cheap human, there is not in, I was just discussing this earlier today with somebody, there is not enough investment in automation because it's still cheaper to export the task to another country, right? So in this sense, human labor is cheap. But then in the other sense, like, we are solving certain tasks with machine learning instead of with, let's say, rule-based reasoning, because it's cheaper to pay a bunch of mechanical Turks to label the examples used in learning than it is to pay a knowledge engineer and a domain expert to generate the necessary rules that you require and test and check the system. So there is a, yeah, sorry, I'll stop the chain of thought right here.
Okay, one last comment is that AI might change some of that. There's already thought about using AI to verify and design hardware. So we'll see. Maybe that will take less human labor in the future.
Automatizing part of the creative labor there.
Yeah,
Yes.
exactly. Or the not so creative, which is like testing different cases and see if they pass or not.
Repetitive part of the creative labor.
Yeah,
Yes.
exactly. There is a question on the chat. I can. So where is the upper limit for HPC?
Yeah, I want to. Yeah.
And I mean, we don't really know. I think there's going to be a lot increase in performance, like in our lifetime. But the closest I can provide to an answer is there's this graph here that talks about the efficiency of so how many operations can we do with 1 joule of energy? So basically operations per constant energy.
Yeah.
This graph is taken from, I think it was a program manager's talk, and that's why you see there was a specific reference to what DARPA wanted to achieve. But the point, Exascale approximately will be able to do 1 giga operations per joule of energy. The theoretical upper limit is 1 zeta operations per joule. This is not 1, this is to the order of. So don't take it as literally 1. But the point is there's many orders of magnitude that we theoretically can achieve. Now, how many can we practically achieve given that the system needs to be programmable and yada, yada, yada? We don't know.
Great. George, until what time will you be able to stay with us? We have a discussion after this session. Will you be able to stay for the discussion?
I can stay for 20 minutes or so.
Oh, perfect. Perfect. So we will have you for part of the discussion. So we can continue with 2 more questions specifically on your topic before we go to a more general discussion. So from the participants, I remember, Bobby, it was you yesterday that asked about the material that is being used for building chips and how is this important today? What are the limitations there with respect to accessibility on these materials from different countries? Is this something that you brought up, or I don't remember well?
Yes, that was something I brought up. Yeah.
I think we have the right person here to address this. No?
Yeah, no, I was actually researching while you guys were talking right now. I don't want to take any too much time. You guys pretty intellectual, but I was just looking up what materials are considered superconductive. But yeah, I mean, who actually knows where those mineral deposits are? I mean, those are probably secrets. I don't know. But yeah, I don't know. Sorry.
That's a good question. I don't have much to contribute to that, honestly. I'm not sure where they find those materials, but I will say there's not just one material. There's a collection of them.
George, building up on this question, and connecting, may I have 2 questions? So one that I wrote down as you were writing this, as you were giving this talk, I kept imagining that, since everything becomes so specific, as you are saying, is this the case that this is not, I would expect that everything will be stored on the cloud, right? And you would be accessing this power performance through, again, a general kind of getaway. So you will have access to everything in a general manner, but there will be specific hardware there available for you. This is what I would imagine, right?
Yeah, well, this is okay, HPC systems tend to be not available to the general public, right? So these systems are available to specific kind of researchers or national labs. So we don't really go into the interface question a whole lot. I mean, obviously there's an interface, but it's not meant to be as user-friendly as you would expect from Amazon Web Services.
Yeah.
If you want to make this available to the general public, then yeah, absolutely, you need something similar to that and a quota system. And one issue that I can see is that you will have to, like, imagine that you have a system with accelerators and a user gives you an application. You have to find out what accelerators are best suited for that application.
Yeah.
So the question is, can you rely on the user to tell you that? Are they not knowledgeable enough? Or do you automatically scan through the application and hope that you make a good prediction?
Yeah, interesting. And I see room for AI there.
Yeah, absolutely. Yeah.
Nice. And what about biological computing? if
Yeah.
I know I'm getting you a little bit out of but it's
it's one of the, I haven't done any work, but I've definitely heard of it and seen some work. I would classify it as one of those exotic things that if they work out, it will be way into the future. So I don't have much to add. So, but I will share another thought. When it comes to exotic ideas like biological computing or even superconducting and all that, the other question is how do you integrate it with a system?
Yeah.
Because you need to sort of make it accessible somehow to people to use. So do you connect it as a component on the network, or do you just create a specific system that is only good for that, like a quantum system is like specifically quantum and does only quantum? I don't have much to share,
Emerges
but
as a question there.
yeah, it's
Yeah.
a different question. I don't know. I mean, there's going to be a lot of economics will probably go into that I cannot predict right now.
Perfect. All right. Any other topic-specific questions before we transition to the general discussion? I see in quantum, KG is asking, and quantum. What about quantum? I guess to some extent George covered this. That it's typically quantum computing is very specialized. Like D-Wave. D-Wave is there any other commercial apart from D-Wave right now?
Fujitsu has some digital annealers. I mean, they're not quantum, but they try to mimic the computational model. I'm not aware of anything else right now. But my thoughts on quantum is exactly as you said. It's specialized, and we'll see. It's not clear how much better they will do than some of the quote-unquote classical computing solutions that we're looking into. But it might work out and be amazing. For sure, it has lots of promise.